Hi, welcome to me313. This video, the purpose of this is a follow-up to the in-class problem that we did just recently, and hopefully this helps elucidate a couple facts based on some questions. I think this might help. The main point I want to make is that the equation of state that we use, which in the class example was compressibility, and the idea of these additive laws like Ohm's law and Dalton's law are two separate things. And I think to help demonstrate that, I'm going to go ahead and quickly go through the same problem we did using a different equation of state so you can kind of see the similarities and the differences. So here what we're going to do, instead of using compressibility, we're going to use the van der Waals equation of state. If you remember that from chapter 3, I'll show it to you here in just a moment. We're going to use van der Waals equation of state, and then we're going to use Ohm's law of additive volumes. So hopefully you can see you can use any equation of state and any type of summing or additive law that you want, and those are the two that we're going to use. So remember the problem that we had. Initially we had this rigid tank with a pound mole of argon. It was at this temperature of 750 psi, 750 psia and 400 degrees Rankine. And then what we did is we added some N2. We added 3 pound moles of N2, and at the same time we went ahead and the temperature eventually drops. You can imagine there was like some fan going on that was removing heat from this, and so after some period of time we'd added 3 pound moles of nitrogen to this rigid tank. We had removed some energy from it, and so at the final state we had the same rigid tank, but now we had 1 pound mole of argon and 3 pound moles of nitrogen in there, and the temperature dropped down to 360 degrees Rankine. And the problem says it wants to go ahead and find what the final pressure is in the tank, and that's what we're trying to find. So here, what I said, what we're going to do is use van der Waals equation of state, and then we're going to use Ohm's law of additive volumes. All right, so to remind you, Ohm's law of additive volumes imagines that I then go ahead and I'm going to have 2 tanks, one with the argon in it and one with the nitrogen in it. They're going to be at the same temperature as my tank, which is 360 degrees Rankine. And what I'm going to be doing is essentially finding what the pressure is in those 2 tanks, which is going to be the same. And I know that these volumes add together. So this pressure that I'm finding in these tanks is going to be the same as the pressure in that tank. And so I can just add those 2 together, the volumes together, and they're going to have the same volume as this much larger tank. So there's the idea of Ohm's law of additive volumes. Okay, so let's go ahead and review van der Waals equation of state. So this is from chapter 3. If you remember, there were these 2 kind of adjustments to the ideal gas law that van der Waals did. It had this pressure adjustment term here, this volume adjustment term here, which are these parameters A and B. Otherwise, it looks like a lot like the ideal gas law. And those adjustment parameters A and B, you can find values for those. And to remind you, you can define those in terms of the value of R and the critical properties TR and PR. And so I give both of those equations here. Now, notice I've got the critical pressure, so there's going to be a value of A for argon. There's going to be a value of A for nitrogen. They're going to be different values, and the same thing for B. And since this whole problem is done in pound moles, what I'm going to do is essentially we're going to do everything on a molar basis, and so those will essentially be per mole volumes that I have. That makes this the universal gas constant, R sub u, and the same R sub u that appears here. So everything's going to be per pound mole. We'll make it all a little bit easier. Okay, so just to remind you, the first step that we did is we wanted to go ahead and find out what the total volume of this big tank was over here on the left, right? Because that remains the same. And so what I'm doing now, though, is I'm going to be using van der Waals equation of state. So I'm going to be plugging in that equation right there and solving for essentially this little v value. I'm given what my pressure and my temperature is. And so what I know is that that volume of that tank is going to be, well, the number of moles that I have, which right there is just going to be the number of moles of argon I have, times that value of V that I determined. This is just 1, and so then I have the volume of that tank. All right, so then we're going to come over, and I'm going over here to the right, and now what I have are my 2 small tanks, and so I'm doing essentially the exact same thing with the 2 small tanks. So for example, let's just look at the argon tank. Right, I'm going to have P plus A over V squared. This is going to be V minus B is equal to RT. Let's call that T2 because there's this new temperature now, 360. This is that final pressure. I'll call that P2. And now note that this value of A and B, those are for argon. So we'll just kind of find those properties are going to be for argon. And then this value of V that I'm finding, this little value of V, that's going to be the specific volume of this smaller tank. So I could say the total volume of the argon tank is going to be the number of moles of the argon tank times that value of V that I just found from that equation. Okay, that's going to be the upper tank. I'm going to do the exact same thing for the lower tank. So there's going to be my nitrogen. I won't write that down again. You're going to be Van der Waals equation, but you're going to have a value of V from that one as well. And then we know that the volume of that nitrogen tank is going to be the number of moles of nitrogen, which times that value of V that I'm determining. They're both going to have the same P2 and the value of V2. Now, there's going to be one last thing I need to note because I don't know what the volumes are or the pressures. There's three unknowns. I have two equations, and what I need right now is a third equation, and that's just going to be say that I know this volume I found over on the left, remember the volume, total volume of the tank, has to be equal to the volume of these two little small tanks. So that's going to be the volume of the argon tank plus the volume of the nitrogen tank. Okay, so notice the only difference from what we did in class is we're using Van der Waals equation of state each time in place of the compressibility. Okay, so I have these three equations, three unknowns. So this is a classic example of our EES, a little easier. So I'll just go ahead and finish solving this problem in EES. Let me just go over there. And let me just show you what we've got. Okay, so up at the top, these are just my specified parameters. T1, T2, the temperature change, my initial pressure, P1. I'm told the number of moles. I'm using that. It's N of argon and N2. Everything's on a per mole basis. So here's my gas constant, R, universal gas constant. That's per pound mole. All right. So first thing I wanted to do is find my Van der Waals constants A and B. Remember, there's different values of A and B for the two materials. So I've got it for argon and N2. And so if you look here, I'm using the T-crit and the P-crit functions within EES to go ahead and get those values. So that's going to give me my values of A and B. And then this is finding my initial volume. So this is that tank on the left, my initial point where it just had argon. And so that's going to be this value of using P1 and T1. And that's going to give me my specific volume, little v1. And I'm going to multiply that by the number of moles, which is just 1 in that case. And then the final step down here is I've got my Amigat's law. Okay. And Amigat's law means I'm going to have my two little tanks. So here I've got the two little tanks, the argon tank and the N2 tank, using my Van der Waals equation of state. They're at now T2 and the value of P2. So notice P2 is the same in both of those, but my specific volumes that I'm finding, I've got V sub argon and V sub N2, those two little volumes. And then the last thing to conclude it. So these are my three equations I'm solving simultaneously. As this last one, which is just adding up those volumes. This is that last equation that I wrote, where I said that the volume of the N2 tank and the volume of the argon tank has to equal the total volume, which was I found using little v1, that initial specific volume, and there was only argon in there initially. Okay, so three equations and three unknowns there. So if we have this right, and go ahead and solve this on EES, and it's able to solve it. So here we go ahead and see our solution. And so the things to kind of point out is, let's look at our pressure. So the problem said find the final pressure. We see it's at 2,500. All right, so that's kind of similar to what we had with compressibility, but a different value, but it's of the same order of magnitude. Notice also at the top here, my values of A and B are different between argon and nitrogen because they're different types of properties. And then also, let's just look at the initial volume. This is little v1. Multiplied by the number of moles, but the number of moles of argon is just 1. This is the same 5.653. So it's a little different than the initial volume we had in the in-class example, but again, it's on the same order. I think in class it was like 5.15, right? So hopefully you see, like, you're getting kind of similar answers. These are all just different ways to give ourselves estimates. None of them are necessarily better than another technique. They're just good techniques to have. I want to wrap up on one last thing here. It's like yet another way to do it using Van der Waals equation. And that what you could do is you could just average those properties and create what's called a pseudo-substance. And the book talks about this, and I'll just review it quickly. If I define a pseudo-substance, what I'm doing now, this is similar to like K's rule, but I'm using my Van der Waals, where I'm going to go ahead and have a mixture value of A and a mixture value of B that I'm putting into Van der Waals equation. And what I'm going to do is I'm going to mass average those, or sorry, mole average those using my mole fractions Y. All right, and so here's the value that it would be for A, and this is the value it would be for B. And the book kind of gives these examples as well. I could do this. This is an alternative way to do it. And in fact, I did that in EES. So let's just kind of go over and look at that. And so if we come down here, I'm going to go ahead and remove these comment brackets so that you can see what I have. All right, so looking at this, here's my pseudo substance. So first I'm defining my mole fractions of Y of argon and nitrogen. So that's what those top two lines are. And now I'm doing my mixture values of A and B. All right, so that's what that value of A sub M and B sub M, those are of the mixture. And then I just now apply van der Waals equation once, and I'm going to go ahead and find my final pressure. I'm calling that P3 here just because earlier we had it P2, but this is again is going to be the final pressure using the pseudo substance material. And then the last thing to close it is that I have to know that my volumes are going to end up being equal to the same. So if I go ahead and solve this now and look at this problem, you can see what P3 is. Using this pseudo substance, it's 2504 relative to 2500. I mean, those are essentially the same. They're within less than 1%. So not the exact same technique, but pretty darn close. So you can kind of realize there's various ways that you can solve this. So hopefully the takeaway that you get from this is that there's two things we're using. We're using equations of state, and then we're using additive estimations. So omegot's, Daltons, K's, those are estimations, and then those are independent of the equation of state we use, whether we use compressibility or van der Waals or any of the others. So, okay, well, hopefully that helps, and good luck.